All right, thanks everybody. So we all know that there's different mechanisms that can trigger tipping points. When I teach this material or when I lecture on this material to ecologists who are not necessarily familiar with anything besides bee tipping, I like to refer to our Saturday morning cartoons to explain bee tipping versus N tipping versus R tipping. And I recently finished the first complete draft for a book that I'm writing that many of you have heard about because I can't stop complaining about how much work that was. And I've made a version of this concept that hopefully will get past the publisher's copyright concerns. Because that's just a coyote. There's no copyright. It's just a bird. It's a picture of a bird. Okay, anyway. So today's talk is going to work through these three categories of tipping points in an ecological model. My title refers to one of possibly two vignettes, depending on how long that takes. I have another little much shorter thing to add at the end if there's time. But we're certainly going to talk about competition and facilitation. And again, time permitting, rate dependent. We might talk about intensifying seasonality. Dive into our first topic. Facilitation is an interaction among species that benefits at least one of those species, possibly itself as well. There are a lot of examples. It's relatively understudied from a theoretical perspective. Competition or antagonistic interactions much more commonly studied. But facilitation can take many forms, including refuge from negative species interactions such as predator protection, making the environment less stressful, improving resource availability, and so forth. Some real-world examples are nurse plants. So this is the saguaro cactus, and these can typically only germinate. Once they're adults, they're pretty robust to the environment, but they can typically only germinate right in the root sphere of what's known as a nurse plant, and other plant around it, which stabilizes the soil and retains water in the upper soil. Other examples can be structural. So mature corals provide habitat protection from physical disturbance to planktonic stages of other species. And there's a lot of examples in successional series. This is an example of post-glacial succession where the conifers can't establish until something that can fix nitrogen in the soil, turn inorganic nitrogen into organic nitrogen has settled. So these are all examples of facilitation, but again, relatively, despite being so common, relatively understudied from a theoretical perspective, but relative to the other species interactions. So in this model that I'm presenting today, it's a simple two-species model. One is what I refer to as a competitor, and one is a facilitator. Both experience intra-specific competition, so they're each self-limiting, but only the competitor, the one I refer to as a competitor, imposes additional inter-specific competition on the facilitator, and then and an example again in the real world would be then sort of this feedback where the nitrogen fixers are facilitating the conifers, but the conifers then might outcompete them via shading. That would be an example. Facilitator in this example mitigates environmental stress, which is just represented phenomenologically via parameter. And it does so for both species. So it has to, the facilitator, there needs to be enough of it in harsh conditions for it to even persist, let alone support the competitor. And we look in this model at the resulting dynamics that vary over a stress gradient. So this is our model. I've had the names of my collaborators on my title slide, but forgot to say them. So Gaku Takimoto first wrote down this model, and then Katie Dixon and I have been working on analyzing it through this lens of tipping points. The model is set up so that, as I said, each species is self-limiting. The facilitator has an additional impact of competition, and then facilitation of the competitor by the facilitator takes this form. And so the idea is if there's no facilitator, there's just a density independent death rate due to, we'll refer to this D parameter, DC for the competitor as the harshness of the environment. So there's something about the environment that's killing these individuals, but that is ameliorated by presence of the facilitator. And importantly, the facilitator does the same thing to itself. And as we've written it, it's possible, we're imagining it's possible for them to have different sensitivities to the environment. So in other words, different D values, but we've only written a strength of facilitation theta as a single parameter that affects both equally. Of course, we could relax that, but we haven't for the sake of tractability. So this model does some interesting stuff. In a mild environment, so that means low D values, the competitor will outcompete the facilitator because facilitation is not very valuable when the environment's not very harsh. I'm going to show a series of these figures with, I think you'd be missing an axis label. This is the competitor density. Again, it's scaled between 0 and 1. 1 means carrying capacity if the environment was not killing anybody whatsoever. Okay, so we can have the competitor alone. We can also have stable coexistence, converging to a stable node, or we also can have stable limit cycles in this model. The interesting stuff starts happening at a sort of intermediate level of environmental harshness where there is bistability. The thick black line is the separatrix between the basins of attraction. There's bistability between extinction of both species and coexistence, again, with or without stable limit cycles. And that is because when the facilitator is too rare, both species, including the facilitator itself, are unable to deal with the harshness of the environment. But if the facilitator is common enough, then they can coexist. For very harsh environments, there is a zone where the facilitator can persist on its own, given that the parameters are set to where it can tolerate and the competitor can't. Of course, then too harsh and everybody goes instead. So those are the various behaviors. This is a bifurcation diagram where I simplified the picture by setting the two sensitivities to the environment equal. So now we have one sort of harshness parameter that's affecting both species. Showing the bifurcation diagram, of course, for the competitor and the facilitator, I should mention, because I looked at this for a while and thinking it was wrong until I realized that some of you might have also been like, that's wrong. There's no stable equilibrium between these two, and it looks like there's an unstable one missing. They're actually, for the competitor, this branch and this branch are both on 0. That's why you don't see. So it's really this one that's more helpful to look at, because you can see the separation in the basins of attraction there. So this is the picture, again, showing those behaviors that we just walked through in state space for moderate facilitation, meaning a relatively, I'm going to show you a series of diagrams where I'm holding all the other parameters constant and changing this theta, the strength of facilitation, making it higher as we go. So this is for sort of, I wouldn't say low, it's important enough that this is a meaningful interaction, but it's not super high. So moderate facilitation, we get the picture that I just walked you through. But for stronger facilitation, we have stable limit cycles within the coexistence zone, which is the green on the top. So we've added these two new behaviors where the cycles themselves are stable. And then this is actually a really interesting one, and I'm going to sort of plop in here, and we haven't done a ton, so the rest of my results are going to expound on this more. But if you make facilitation strong enough, then the limit cycles crash into the unstable branches of the facilitator only equilibrium, and of course we get extinction in that case. So there's this little window where the oscillations are too wild, which is pretty interesting, non-local bifurcation. Different from what Chris talked about yesterday, which probably you all know, but I had a quick chat with him over beer last night to talk about why. Okay, so those are just sort of pictures. The boundaries between these states depend, of course, on the parameters. So the competitor will persist alone if the environment is harsh, is mild enough, in particular, mild enough on itself relative to the, that's a typo, that should be an F, relative to the facilitator, and if its competition is strong enough. That's what allows it to exclude the facilitator. Extinction is stable whenever the environment is sufficiently harsh, and the way you scale it is when these ratios of the death rate to the intrinsic growth rate is greater than 1. And this is the key to what, the interesting stuff that happens, because extinction is stable for all higher values, and that's not a particularly harsh environment. I mean, it's quite intuitive that that's what happens, if you look at the equations, but, sort of no matter what the facilitation is, it's always possible for these things to be stably extinct. There's this window where the facilitator can persist alone, and that again requires its sensitivity in the environment to have some relationship relative to the competitors and its strength of facilitation. And in between these, I haven't written the stability conditions for like where we get the cycles, if we get the cycles, because they're really gross, but this is the equilibrium that we see. And so just looking at the bifurcation structure of this model, we of course see many potential areas for B-tipping. And just throwing one of these, the one that shows all the behaviors up here, if we think of B-tipping, like if we're in a situation where the environment is getting gradually more mild, I say gradually to indicate that we care about the equilibrium, the system is likely to be near it. If it's gradually getting more mild, we have the possibility of facilitator extinction. That's quite intuitive. If facilitation is less important, perhaps the competitor is fine without it and can outcompete the facilitator. But counterintuitively, in the situation where we have this non-local bifurcation, both species could go extinct if we're making the environment mild, or if we were in this zone of coexistence and improve the environment in that direction. And that's something that, again, is not intuitive from an ecological perspective, and I think quite interesting from an ecological perspective. If the environment gets harsher, of course, the competitor could go extinct, or both species could go extinct. And now we have two ways to do that. We could go from where they were coexisting again into this zone, or we could go from where they're coexisting here into this zone. So two ways to cross bifurcations into extinction if the environments get harsher. Okay, so that's sort of the easy one. I mean, B-tipping is, I think these are some interesting results, but B-tipping is sort of like rough and ready. We know B-tipping. I was really interested to look at rate tipping in this model, asking the question, and you all know the answer to this question is yes, does the rate of environmental change matter? So do we see something different when the environment is improving or worsening at a rate that's fast enough that we can't just assume for simplicity that it's tracking the equilibrium? And then an interesting question inspired by some of Alan's work with collaborators is how does our answer to that question depend on the initial conditions, where the system was before that environmental change happened? Because we don't expect ecological systems to just be sitting at equilibrium. There's lots and lots of noise, lots of reasons, even without, a systematic harshening or milding of the environment, there's lots of reasons to expect that we're not just sitting at the equilibrium point. So we have to consider both how quick is the change happening, but also where were we when that change began. So for the moderate facilitation case, the first one I showed you, and I'm just showing the facilitator bifurcation diagram here because it's easier to you can see more information. What I'm going to do in the what I'm about to show you is gradually increase the harshness of the environment from 2.5 to 8.5 over 25 years. And importantly, if you look at the top in my little color code, it's always staying within the coexistence region. But it's the region where there's coexistence and, of course, stable extinction as a possibility. And if we start in the basin of attraction of extinction, it's not very interesting. But if we start in the basin of attraction of that coexistence equilibrium, and start not right at it, but relatively close to it, we see that as the parameters change, as these D parameters change, the harshness, and again, for simplicity, I'm showing with the two species equal, but we can, of course, relax that. The video showed that as the separatrix, the basin boundary for coexistence, pinched in, the dynamics were able to keep themselves within it and track that equilibrium. So here's a case of no R-tipping. My collaborator Katie Dixon has been doing some stochastic simulation of this model using the tau leaping algorithm. And although we will talk about N-tipping, but we're not yet. I just wanted to show what sort of a more realistic, little bit of noise in the system, what this looks like. And again, even with a little bit of noise, we've kept the noise intensity small enough so that if it tips, we think it's R tipping and not N tipping. But anyway, this is what it looks like for those that prefer to see the information in this sort of format. But of course, same exact scenario, same increase in environmental harshness, same rate of increase in environmental harshness, same parameter values, we're still at moderate facilitation, but different initial conditions. Now we're going to see here, in fact, quite fast rate tipping, because the orbit that was trying to take the system into the equilibrium point crossed the basin boundary as the basin boundary pinched in. And it doesn't know, depending on where we start, it doesn't know. It can sometimes make a few cycles, but there are many situations where the cycles take us outside the basin boundary. So again, inspired by work by Alan and collaborators, we looked at a grid of initial conditions. This, where it's white, that's in the extinction states bound of basin of attraction. So we're not looking at initial conditions there. We're interested in initial conditions in the basin of attraction of the coexistence state, and asking if we start the system there, and then change the environmental harshness at that rate, 2.5 to 8.5, 25 years, the same situation we've been looking at. So of course, all these results are specific to those choices, right? But if we do that, and this is the actual stable equilibrium point before the change, this is all with no, sorry, I just said we changed it from 2.5 to 8.5. Yes, we did. This is the equilibrium at 2.5, sorry, before the change. But the color coding is, did we tip or not from those initial conditions when we then change 8.5 for 25 years? We see, and in this case, there's a pretty simple, I mean, we wouldn't know this exact shape, but it's intuitive. It's what you would think. If you're close enough to the equilibrium, those transient cycles trying to get you back to that stable point are tight enough that they don't cross the basin boundary. But what we are interested in is, okay, so we could just compare, dark red to yellow and see how much of the basin would tip, right? And that is completely fair to do, but we were interested in how likely are you to be in some of these yellow spaces far from equilibrium in the first place. Are we likely to be in any of those yellow states where they would tip? And so what Katie did was this tau leaping algorithm that runs the model with a little bit of noise. Again, sort of, now my results are specific to yet one more thing, which is our choice of the intensity of the noise. More intense noise would spread out that blob. But for this parameter set, and this is just at 2.5, the environmental harshness before any change, she's shown that you're quite likely to be near equilibrium. Of course, less likely if we add the noise, but I think we can see the geometry of this. And so then what we did is we multiplied these two things. So if you're not going to be in a state that tips, it doesn't count as tipping risk, right? So we multiplied those two graphs and added up everything shown here. Of course, we could extend beyond 1, but we haven't. That's a bit arbitrary, but it's zeros out there, so it's not a problem. And we see that, in fact, despite all the yellow in this first figure, we're very unlikely to R-tip, again, for this level of noise, which gives us this distribution, and for this rate of change in the parameters, which gives us this. So, so it's an example, right? But I think it's a pretty compelling example that actually the amount of yellow in that first diagram is misleading. In this particular case, we're not very likely to R-tip because we're not very likely to be in any of the states that can R-tip. Taking ourselves to the next example where we have stronger facilitation and the possibility of cycles. Again, we can R-tip or not. This is an example where we don't. It's just raising that separatrix as it comes in, which is what we see. So that's not probably particularly robust to noise, and we're going to talk about noise next. And we'll wait. This is a stable limit cycle. It's working its way in. It takes a little while. So this is the case where we don't R-tip, but of course there's also situations where we do. It makes it a cycle or two, and then process. So this situation is actually a lot more interesting. Now the stable limit cycle before the change is shown by this black outline. And then otherwise the color coding is exactly the same. So we see if we're inside it by enough, so that when the change begins, the oscillation is still pretty tight in here, then it's safe. It's not going to crash the boundary. Interestingly, we have this arc where it's like, it gets around just at the right time. So it's not at this part of the cycle as the basin boundary is pinching in, which we think was very interesting. On the stable limit cycle itself, we do get tipping. So I do think it's p-tipping in that case. Maybe. No, damn it. I thought we talked about this last night and I was convinced it wasn't p-tipping, and then I actually added this orbit last night because I realized I wasn't sure exactly where it was. I actually thought it was around the red. So you do tip from the stable limit cycle.
Just to clarify that,
yeah,
you start at an equilibrium state and then you change your parameters so that you get Hopf bifurcation throughout, and then you try to track a limit cycle.
Everything you said is correct except start at the equilibrium state. I start at the pixel in this graph.
Yeah, but
anyone.
The stable state would be an equilibrium state. You don't start at it, but
correct.
Okay.
I could start. If I happen to be on that orbit, I started at it. But everywhere else, and it's of course discretized state space, so maybe I never start exactly on it. But yeah, so this is all. I start in one of these initial conditions, and then impose the change and see whether or not it
And does the limit cycle exist for the parameter where you start?
Yes. Okay. We're going to have a follow-up discussion about p-tipping. Okay, but anyway, so we tip, and this is a more interesting picture, right, with that outer orbit. And then it's also more interesting because we are quite likely in, and this doesn't surprise anybody that looks at stochastic models, when we add a little bit of noise, again, relatively low noise intensity here, so we could change the picture quantitatively by changing that. But when we add noise, this is the part that won't surprise anybody that's used to looking at stochasticity in cycles, we have some variability. It gets pretty faint, but we have a fair amount of variability in how high the peaks of these cycles are, but we're quite consistent on hitting the same trough. And so that means that the probability of being somewhere, around here, even with noise in the cycle, is quite high. And so putting it together, our overall chance of p-tipping, our overall chance of being in a particular state and then p-tipping from that state is quite high in this example. Okay, so to our knowledge, this is a novel way to represent p-tipping risk, although I'm interested if there are related methods that I should be aware of. But anyway, we're pretty interested in this kind of result. So to summarize this piece, we see R tipping in the situation, well, so stronger facilitation, that was the non-limit cycle. The limit cycle example is we made facilitation stronger. That makes the system more vulnerable, meaning, I forgot to even point out, I made the same change in the parameters when we switched to the limit cycle case, but I made it actually quite slow. It was on my slide, some of you probably spotted it, but I changed it from making that change over 25 years to making that change over 50 years, because if I do it over 25, then I'll toast. So implicit in the thing I forgot to point out to you is that overall, the rates need to be slower when you're cycling. And again, that makes sense. The excursion, towards that separatrix is bigger when you have a stable limit cycle, and so it's more vulnerable. And then acknowledging this is not a result, it's just a statement. Real systems are likely to be away from equilibrium, and so understanding how likely they are to be at a particular state before a change, I think, is significant. A lot of very nice R tipping work just looks at the probability of R tipping from the equilibrium state, and that's extremely compelling. And I think this is sort of an additional layer of understanding how to take that compelling result to the real world. Okay, those are the first two ways to lose a friend. The friend is our facilitator. That's where my dumb title comes from. So we have B tipping and we have R tipping, and of course the last one is N tipping. This will be a little bit of a disappointment because this is the work in progress. This is the piece that Katie's working on. She's doing all the stochastic work. And And so I'm just going to give you a little flavor of what we're finding, but I don't have full results here yet. Entropy, of course, can occur with or without a change in the parameters. So it's sort of always there. We have bistability for a lot of parameter values. So of course, it's in any part of that range, it's a lingering threat. And in this situation, we started going into n-tipping and just started thinking, yeah, we should run some simulations and show it just so we have the full set, right? And then it ended up being really interesting. And so what we're finding is actually a potentially interesting counterexample to what's known as in ecology as response diversity theory. Response diversity theory is the idea that in a community, anti-correlated species responses to perturbation, stochasticity, sort of whatever, species interactions for that matter, can be stabilizing. And the idea is that it just, if species are sort of functionally redundant in some way, and they're responding in an anti-correlated way, when one's up, the other's down, and vice versa, and we're unlikely to have everybody sort of crash out at the same time, and that's the concept of how it's stabilizing. But our preliminary results are actually showing that if we put in some noise, the results I've showed you so far that came from Katie's work were with uncorrelated noise, meaning each species growth rate was perturbed a little bit, but into IID of one another. But we can build in correlation in how in any particular point in time, how are the two species responding? And if they respond in an anti-correlated way, with a negative correlation, we actually find that increases n-tipping risk. And we can understand that by considering the shape of things in state space. So if we're somewhere near this equilibrium and the growth rates are varying, this is a very heavy explanation, but I think it's intuitively will make sense. We have not dug in carefully to be sure that this is what is happening, but because it's kind of maybe because these are, of course, densities on the axes, and I'm talking about growth rates varying, but roughly speaking, growth rates that vary in a correlated way will move the system this way in the state space. And if they're anti-correlated, they move this way in the state space, and of course, this is the direction of the separatrix. And so what we're doing now is digging in deeper to how the correlation structure in the noise affecting the different species changes n-tipping risk, both with and without parameter change. So what we thought was going to be kind of a throwaway, just complete the set, actually I think is going to be potentially the most interesting part of this paper, but unfortunately for you guys, I chose to speak only about work in progress to how those results. So the highlights so far, meaning conclusions from this first piece, are that gradual improvement of the environment could lead to extinction of both species. That's sort of the most interesting to me, biologically interesting result. That's the bee-tipping result. So that's the biologically most interesting bee-tipping result. Stronger facilitation promotes species extinction of both species under, when I say faster environmental change, I mean in the R-tipping world where we're not necessarily tracking the equilibrium at this point. And anti-correlated responses to environmental noise promote extinction of both species. That's an n-tipping result that I've only just given you a flavor of. And then I think, as I said, new but question mark, tell me what else I should look at, approach to quantifying R-tipping risk by taking the idea of looking across initial conditions, but then weighting them by how likely the system is to be found. I do potentially have time to go into my second piece, which is much shorter than my first piece, but I'll pause here and take questions on this first part, I think, and then we'll see what time it is. Yes.
So you have this of extinction, this interval of extinction.
Yeah.
If the rate of change is very fast, could you jump it? So you go boom, and you don't get extinction because you get on the other side before it happens. It means if the environmental change is fast enough. You only look at slow changes, didn't you?
Medium scale. Let me go back to this picture. I think the answer to your question is no. Well, I guess it depends on where you are in state space, right? But
you'll be on the left, and then you
instantaneously you do cross. This is for this, we're only looking at one of the variables. But if you're somewhere on this cycle, maybe if you're at the very top, you don't. Yeah, there might be places where you are. The moment of the instantaneous change. perhaps you can escape it. Yeah, I'll look at that. That's a good question.
I have a general question
Yes.
on the exploration strategy.
Yeah.
How do you go through this big parameter spaces? Are the trajectory so fast to compute you can just sweep, or
Yeah, yes, we can sweep the initial conditions. That's fast because in the results, in this style of results, we got yeah, I've been methodologically a little brief. This is from the deterministic model, so it's very fast. This is from a stochastic model because otherwise you just have 100% probability of being on the attractor, which is not the ecologically realistic thing we want to look at. We want to look at if you're not quite on it, where are you going to be? This is also reasonably fast because Katie's a wizard, but I can't say a lot more than that. But you know, still, this is one parameter set, sweeping rates.
Right.
And our exploration strategy there was to do the bifurcation analysis first, and then pick out interesting parameter sets to get a more general answer for both R tipping and N tipping. Yeah, is either going to take a lot more computation or cleverness. But right now we're doing essentially what we think are compelling case studies pulled from the bifurcation analysis. That tells us sort of where to look.
That
for
makes
those case studies. Yeah.
Thanks.
Yeah.
Okay, can you go please to one of your first slides with diagrams, bifurcation diagrams,
Yes.
where you have extinction, both species, somewhere in the middle.
Yeah.
No, maybe.
Is that one okay? You want
next slide?
that one?
Maybe next slide. Oh, yeah, this one. Just to continue this question about fast and slow or tipping. So if you have, this region is the extinction rate.
Yeah.
This one. And I wonder whether or not you can consider fast and slow.
Yeah, that's a great question. We have not done any more with this case than just that. We haven't taken this case past just bifurcation analysis. But I am really curious what we'll do. So yeah, to be determined. Great question. I have no idea. Did I see a question over here? Yes.
A very rich model. So it's a very nice question, and I don't know the field at all. So when you get this picture and some for this interesting phenomena to go to extension with a lower facilitation, can you go back into the real world and try to describe if this happens actually? Or?
Yeah. In a direct sense, I will be honest and say probably not. Simply because strength of facilitation, well, I don't know. I'm not an experimentalist, and maybe a clever one would tell me that this is too simple-minded. It seems like strength of facilitation would be a difficult quantity to manipulate. So like the gold standard manipulative experiment. I don't know. To do something where you look across either environments, the same species pair in different locations, or different species pairs with different strengths of facilitation, you might be able to find sort of observationally that the real world is consistent with this. A direct test of this result, I guess I was going to say, no, but maybe it's just because I'm not imaginative. I'm not an experimentalist. It's an interesting question. Yeah.
So this may be way off topic, but essentially, if I were thinking about this, I would think you've got your facilitator and you've got the essentially an environmental state.
Yeah.
And if you had made that explicit, you'd sort of be talking about that as an ecosystem engineer. I know some people use it. And what you've done is essentially assume that ecosystem engineering dynamics is of a particular form.
Yes.
Where it's essentially has to be continually maintained, and there are explicit models. Done some of them where you actually do ecosystem engineers. We've got the one species one. We didn't extend it to two, but this could all be interesting to put that in explicitly and get some very interesting dynamics.
Yeah. So you're talking about having the environment be a state variable?
Yes. That's the same.
Because I'm essentially
you're essentially assuming
Doing that and assuming it's instantaneously changing.
yeah, you're
Yeah.
assuming that the
It's
environment
tracking
is a state
facilitator.
variable, but that
Yeah.
it's on a faster time scale.
Yes, it's perfectly tracking the facilitator density. Yeah. Cool. Well, that's the next project for me and Katie, I guess. I like that idea.
Yeah, we should
Yeah.
talk more.
Yeah. Yes. Question.
Yeah, I would be a bit cautious with those cliff drawings about tipping points. And
Just went to the publisher. No.
before you talk. And the reason is because tipping points are nothing like falling off a cliff. Actually,
They're slow. Yeah.
What happens is that you have this big B tipping. People call it critical slowing down. If you go past the bifurcation point, you move slowly because the dynamics is non-exponential level.
Yeah.
You have plenty of time to return.
Yeah.
So you go over the cliff.
But you don't look down.
A lot of time to change your mind, reverse
Yeah.
the parameter and be rescued.
Yeah.
The same is true about the rate tipping and the rate phase tipping which you have here.
Yeah.
That if you sort of reverse the parameter change a bit faster than maybe it grows,
Yes.
you can recapture and rescue the system. I would call it like rescue events.
Yes.
Where you sort of capture the basin of attraction of your coexistence state or the normal state.
Yes.
So just a comment about this.
No, you're absolutely right. I didn't.
I don't like falling off a cliff.
Yeah.
All the pictures of
I'm
cliffs.
falling off the cliff. No, okay. To be fair, that yes, yes, I'm aware of that, and well, I'll go back and be more and double check. But with my work on long transients, it's a thing I think about a lot in a different way, I'm sure. But the rest of the chapter is about what happens when you
Maybe
fall
the
off the cliff.
publisher knows about this.
Maybe the publisher knows about this. Well, yeah. So the idea is if the coyote doesn't look down, he doesn't fall. So he has time to turn around and run back. But yeah. No, point well taken. Yes. There you go.
So in your example, since you have this rotating movement
Yes.
in state space, so it can happen, of course, that your trajectory traverses the boundary
Yes.
more than once. So because you can go back and forth going over the boundary. So did you study that and look at really in state space? Because the critical rate, so to say, for tipping in a rate-induced tipping depends on your initial condition.
Yes.
So, but then
Yes.
of course, how often you are so to say going over the boundary plays a role in your case.
Yes.
And did you look at this kind of relationship?
Not yet, because most of what I've shown today, the sort of division of labor was I was doing the deterministic and Katie was doing the stochastic, and you can only cross multiple times in the stochastic case. In the deterministic case, in the deterministic case, if the boundaries
For stationary solutions you can, and for oscillatory, I would say you can also. It depends on the timescales. It's very closely depending
Yes.
on the time.
Yes. Okay.
Of course.
Yeah.
I'm aware of this.
Yes. We have not looked at that. We've thought about it in the case where the multiple crossings are due to noise. But we have not thought about it in the case where it's due to time scale. So thank you. That's great. That's a great question. Okay, in my little bit of time left, as I said, my next vignette is much shorter than what I've just shown you. This is shameless. I added the second topic that has nothing to do with my titles. We talked about losing friends. But I had there's another, I'm just showing you guys work in progress because I feel like that's the most, maybe I'm just being selfish, most useful for me to discuss. But I hope it's also interesting to you guys and it's stuff that you can't tell just by going and reading papers. So I had one other thing in that category that I thought this would be a good audience for. And so that is the idea of looking at rate-dependent tipping in seasonal systems. This is something these guys in the front row and I and our working group have talked about a little bit. So the idea is that if seasonal abiotic conditions, so something like temperature, highs and lows are getting more extreme, but the year is not getting longer. And so the rates of change between high and low and high have to be faster. The only way to get from A to B within the same amount of time. And so what we've been curious about, what our working group has had discussions about, is whether seasonal ecological processes that are getting more intense with seasonal fluctuations could induce arctic. And this is an idea that was just floating around since our discussions. And then a couple of winters ago, I taught at a summer school. That sentence makes sense if you cross the equator. In Brazil, Christina was there as well, and I met these two students who were working together on a model of this wild rice system. Teo is an experimentalist and works on this rice species, and Jan is a computational guy, and they were interested in modeling what happens with this species. And after my lecture in their course about R tipping, they came to me and they said, "Is this what we have?" And I thought, "Oh, this is perfect." So we've been looking at this system. The idea here is this is a floodplain species. It's a wild relative of domestic rice, so there's quite a lot of interest in it. In potentially finding traits of the wild relative that could help with agriculture. It's native, this species, to South America, and it inhabits floodplain lakes in the Brazilian Amazon, which is Teo's study system. It's an annual. And it has to grow and reproduce entirely during the flooding season. The growth phase is as the flooding begins. So instead of temperature, we're thinking about water depth here as our seasonal driver. And we can model the change between high water and low water, just very simply using a sine function. And of course, if we change the constant in front here, it increases the amplitude of oscillation. But we're interested in isolating the effect of rate from the effect of amplitude. So we actually, in this work, have truncated our sine curve so that it always has the same maximum, but it can do that with different rates. And once you truncate, then this amplitude parameter essentially is a flood rate parameter. And so we call that that's the parameter we tune to talk about the rate of flooding. And so we've made a sort of piecewise OE model. And so for our model, it's just the time period of this thing. We have our model of water depth change that we can manipulate that rate without changing the maximum depth of the seasonal oscillation. Which of course in the real world, right, the maximum depth is increasing as well, but we're interested in isolating this effective rate, so we take that out. Our model is sort of set up like this, so we measure everything in relative elevation from some 0 point to whatever the maximum depth that the shape of the floodplain can hold. And during the flooding season, the rate of change, year-round, but we're interested in the flooding season, the rate of change in the water depth is what we just talked about. And then we have another model for growth of the plant. And interestingly, the growth of the plant, so we're calling H its height, and this, as I will show you on the next slide, this plant grows as a function of its height above the water. It responds to water depth. And so this is an experiment that shows that plants that are dry, so this is in the air-grown state, there is no flooding. This is just like in a greenhouse, so there is no flooding. They're alive and well, but they're not growing. But as these experimentals increase the water level, adding water every day at 3 different rates, we see that the plant adjusts its growth to keep its head above water. So we model the growth rate as a function of how high the top of the plant is above the water depth. The data, when we put it, same data but on these axes, looks pretty linear, not a lot of evidence that we should deviate from that. So we have a linear growth rate within a range, but there is a maximum depth, which they can be a little bit underwater, but they get anoxic, they run out of oxygen if they're too deep underwater and they'll die. And if they're not submerged enough, they'll be alive but not growing, as we see in the first graph. And then so we just have this piecewise linear growth function based on the data. Okay, so putting those together and running through time, and again, just looking at the first part of the year, because this thing grows during the onset of flooding. Water depth is following the sine curve there. Here, I've kept the amplitude parameter low enough that it's not truncated, as you can see. And there's this envelope of depth that if the plant's top is within that, it's growing, and otherwise it's not. So below it, it is dying because it's submerged. It doesn't die instantly, but it will die within about a month, and by the time the waters recede, it has died. Or it's not growing because it's not submerged enough. And so plant that's beginning, a little germinating seedling that's beginning at a particular elevation on this landscape, won't do anything until the floodwaters reach it. So there's a time at which growth begins and a time at which it stops, because as the water recedes away, it enters this air-grown state and stops growing. This is the same picture But in the case where I had to truncate the curve, and of course everything's the same except the time where growth stops is now determined by this truncation as opposed to just the whole curve, shape of the curve. And we see that if we make this flood rate parameter high enough, this window, this amount of time for it to grow just gets smaller and smaller and smaller as we increase that amplitude, and these things get steeper. Rate dependence, what we're talking about. And so this is the case where it starts growing, but it can't grow fast enough to exit the envelope, and then it dies. And so what we've done very simply is look at, in this space of the flood rate parameter plotted against the location in the landscape of a particular plant, there's a range where kind of no matter what, it's going to be too deep to live, and a range where it's going to be too out in the air to grow. But in between, we see this rate dependence where whether it grows or survives depends on the flood rate parameter. Okay, so it's quite a simple model, but it's a cool, because we have this sort of empirically derived growth data. It's a pretty compelling story that this is a thing that could actually happen in nature. Of course, if then we need to take off the truncation and actually also account for the fact that they'll be deeper. But just given the rate, it can have an effect on whether plants grow or die. So this is rate-dependent survival of an individual. And then we're also interested in rate dependence at another scale, so at the scale of the population. And so this is work in progress. Jan and Theo, I think, are running these results right now. But we're interested in how this individual, well, obviously the individual level tipping will scale up to the population. If all of the individuals are tipping to death, then the population goes extinct. But we're most interested in the situation where there's another rate of interest, and this is how the flood rate parameter is changing from year to year. So another time scale and another population scale. And we want to know, how do the population dynamics respond to the rate at which flooding intensifies? So I've just sort of imagined individuals in different flooding regimes, but now the question is, what happens to the population as the flooding regime is changing from year to year? And this is work in progress, but what the guys are working on right now is to imagine that the floodplain is just, a nice symmetrical bowl so that we can do some math on it. And then just imagining there is a zone of viability for the individual. So we're not looking at rate tipping of individual growth. But the question is, if the zone of viability is moving kind of upslope with the flood rate, we know there will be. It might be preposterously fast or preposterously restrictive of the biology. But we're sort of interested in what are the conditions where a population that's here can't track the viability zone. And so even though there is technically a zone where individuals could live, there's no seeds being dispersed there. The population goes extinct because of rate dependence of a different origin. Okay, so that's the highlights from the first half. I put it back in case it triggers anybody that had a question that didn't ask it yet. And the new, again, all work in progress, so not firm results, but highlights so far. We see that faster seasonal flooding can lead to plant death, even without accounting for the fact of increased maximum water depth. We think, but it's work in progress, that faster seasonal flooding may also lead to population extinction independent of the risk to individuals, or in addition to, I should say. Again, we think this is novel ? You guys are the audience to ask. We think this is the first demonstration of R-tipping due to increasing seasonal extremes, but I've not extensively looked for other examples, so I would love it if you guys do my work for me and tell me what to read. And then another thing that I think is, at least it's I don't know how compelling it is to mathematically speaking, probably not terribly, but from an ecological perspective, it's actually very compelling that we have these two different origins of R-tipping risk at different scales, both temporal scales and levels of organization. So that's what I'm working on these days. Thank you guys so much for listening, and please let me know.
Questions, please.
Yes.
Maybe about the previous slide about that circle with those different zones.
Yes.
So we were looking at the problem. It's a simple hypothetical problem in ecology where you have a population in space
Mhm.
in what we call a good habitat, and the habitat is drifting over time.
Yes.
So that's exactly
Yes.
what you have here. So you have a current good habitat, which is your green circle, and then the conditions change, environmental conditions change, and the habitat moves to a different geographical location or
Yes.
spatial location. So there's some results on that. I know that Alan also did some experiment with bugs in boxes where he was moving habitats. So,
Yeah.
some time ago. But there's some work on it. I think it's very, very interesting.
Yeah.
Because the results are for population to collapse. I mean, the only reason that individuals can move is diffusion. So it's
Yeah.
for plants,
Yeah.
for example. So
Which is probably fair here because they release seeds into the water and
yeah,
they just sit there and settle.
applicable here.
Yeah,
So
yeah.
animals can run around.
Yeah.
So to get the extinction,
Yeah.
you have to move by far enough. That's one result, and of course there's a critical rate once you move by far enough.
Yeah.
Yeah, so there's been some work in one dimension, just
Yeah.
a simple conceptual model about that. But
Fantastic.
I think that looks very similar to sort of
Absolutely.
the problem we were looking at.
Yes. Yeah. Thank you.
Okay. Any other questions?
Yes.
I've also more a thought regarding your first part.
Mhm.
I found it interesting that you combined the probability of where you are in state space with the tipping risk. And that reminds me a lot of the quasi-potential in
Mhm.
stochastic systems, which does depend on the correlation structure of the noise that you put in there. So that could be one way how to study more systematically how different correlations change that probability,
Yeah.
because you get different quasi-potentials then for different covariance matrices of your noise.
Yes. Yeah, that's a really good idea. That's a really good idea. I think that would formalize the, when I sort of had the flat diagram of state space, and I was like, we're moving this way, right? But looking at that on a quasi-potential would be a way to formalize that.
Yeah, I guess it would still be in the weak noise limit, so it would not be the full story, I guess. But it would be one
Yeah.
way to formalize.
Yeah. Cool. Thanks for that idea. That's great. Yes.
Yes, I'm building on this. In fact, if you look at the quasi-potential, you bring together drift and the noise correlation. So basically, it will tell you the full interaction
Yeah.
of the system and also allow you to see if you have transitions, noise in the transition, it might change dramatically by changing the structure of the noise.
Yeah.
So somehow it could be, so if you think in terms of competition or collaboration of species, is a sort of typically sort of a linear feedback analysis, right? In some sense, that's how you cast them. But then you would see how these integrate
Yeah.
through the possibly very nonlinear drift and the possibly complex correlation.
Yeah.
So, and then you see the net effect, which might not be immediately related to the linear feedback.
Yeah. Hopefully not. 'Cause
Otherwise,
that's interesting.
then it's more interesting,
Yeah.
but it's harder to explain. Then your publisher might be.
Yeah. Yeah. Thank you. Yeah, that's an awesome idea.
I have another question. Can we go to the slide before this one?
Yes.
If we have too high, too low, you have this diagram.
Yes. Yes.
Too low, too high. That's right. So if I were to extend the rate parameter all the way to the left to 0,
Yeah.
then between your top stripe and the bottom stripe, I will have green everywhere, right? Because if it's too high, you die. If it's too deep, you die, and you only live in
Yeah.
between.
Yeah.
So now if I look at this diagram, I almost see like 3 different scaling laws. Between 0 and about 12, there is this sort
Yeah.
of law-raising situation.
It's like,
Yeah, between 12 and let's say 15,
yeah.
very steep, and then above 15, flatter. Have you thought about this? What's going on?
No, but I will
Yeah,
now.
that's interesting.
Yeah.
To understand.
Yeah. Absolutely. Yeah. Good observation. This is why I showed you guys. Yeah, this is fantastic. Thank you. All right. I think I should stop taking questions. Yeah. And hand it over. The schedule said 10:25 instead of 10.
Yeah, okay.
Well, it's the schedule. I noticed it said 10:25, not
Alright,
10:30. So
okay, yeah.
I'll show it.